This is the beginning of Chapter 3 on probability. If you'll recall from Chapter 1, probability is the mathematical study of randomness. Section 3.1 is about the terminology that we're going to use. So a lot like the beginning of Chapter 1 where we had definitions and new terms, we're going to do a lot of that in 3.1. Some of them are pretty involved. Some of them have a brief definition, though. A probability experiment is a planned operation that's carried out under controlled conditions. And it has an outcome that's not completely known, but we can hopefully say all of the possible outcomes. That's actually the next term that we'll look at. Outcome. An outcome of a probability experiment, or just an outcome of an experiment, because that's the only experiment we're talking about, is a result of an experiment. And I'll have an example in just a moment. But for the outcome, the sample space, capital S, so sample space, is the set of all possible outcomes. So everything that can happen in our experiment, that set of all those different things is denoted by S, the sample space. So this can be a list, a tree diagram, and we'll see how to use that, a Venn diagram. Sometimes a verbal description, but we want to be able to change that into something more symbolic so it's easier to write. So my example to demonstrate some of these things, the experiment in this case is to flip a fair coin once. And just an ordinary coin, so one that has heads and tails. A fair coin means that it's going to give heads half the time and tails half the time, or it's equally likely to get either heads or tails. We'll talk about cheater coins later a little bit. You can design a coin that's made to come up heads more often than it comes up tails, for example. But here, a fair coin, in this case, the sample space S is equal to the two possible outcomes, H and T, H for heads and T for tails. So there's only two things that can happen. This is the whole sample space in this case. To go a little bit further in this terminology, an event, so not exactly the same thing as an outcome, but an event is a set of outcomes. In this first example that we saw, there's only two outcomes, so there's not really much to look at. So consider this example. The experiment is this. We're going to roll a fair six-sided die once. So die is the singular of dice, the little cubes with the numbers 1 through 6 on them. So a fair six-sided die is a die that's not loaded. Each of the 6 faces is equally likely to come up on top. And so in this case, the sample space is those numbers, 1, 2, 3, 4, 5, and 6. Those are all the possibilities for those are all the outcomes of this experiment. And this one's a little bit bigger sample space. I can actually define event E, a set of outcomes. So E is going to be an event that includes 2, 4, and 6. So those are 4 different possible outcomes in this experiment. Three different possible outcomes in this experiment. And you could also define this as an even number is rolled. So you could give it as a verbal description, or in this case, you can give it as a list. It's small enough to actually write it down. So that's an example of an event. It's not an outcome. It consists of 3 outcomes. You could have an event that consists of a single outcome, in which case you could just call it an outcome. But an event like this is a combination of outcomes. So I have another description for what the word probability means. Other than the subject of studying randomness, probability as a number has a specific meaning, and it's probability is the probability of an outcome. Is the long-term relative frequency of that outcome. And we're going to get a better feel for it than this. This is accurate, but it's kind of wordy. It's the long term. So imagine the coin flip. If I flipped the coin 100 times or 1,000 times, that's kind of long term. And I would expect to get about half heads. That means the relative frequency of heads is 1/2. If you think of the 1,000 coin flips, about 500 out of 1,000 will be heads. And the more times you do the experiment and measure the outcome, the better you get in terms of long term. The closer you get to the long term relative frequency, that's the probability. We're going to use more mathematics and reasoning than actually doing experiments over and over. So next, though, let's look at the notation for this. And it's going to make it easier to write, for one thing. First of all, I'm going to start writing prob for probability, because that's a long word and we look at it a lot. But probability function notation. Function notation you will have seen in algebra to some extent. F of x is usually how it's presented there, or g of x, or of x is the idea. Here, it's the probability function, and we're only looking at one probability function. There's only one function. We're going to use P of A. P of, so P is the function for probability. A is an event. P of A is the probability of event A. So the notation is this, and it describes the probability of that particular event. And let me give you some more detail on the properties of that function, and I think it'll start to look a little more familiar. So the probability of an event, A, is between 0 and 1. It's what you'd probably think of as a small number. It's not negative, it can't go below 0. But a probability can never be above 1. In fact, these two correspond to, I guess, 0% likely and 100% likely. And those really are the numbers. 0% is 0, and 100% is 1. The probabilities that we're going to use, though, we're going to actually use numbers between 0 and 1, not numbers between 0 and 100. Although if you change it to percent, that's exactly what you would have. There are a couple of terms for those kinds of probabilities, the extreme values here. First of all, the impossibility is when P of A is equal to 0. There is 0 probability or 0% chance of this happening. It's called an impossibility. It just means that event A never happens if the probability is 0. On the other hand, a certainty is something that's guaranteed to happen, 100% chance of happening. That's when P of A is equal to 1. That means that event A is going to happen no matter what. For example, if you took the probability of the whole sample space, one of those things has to happen. So the probability of the whole collection of things, one of them happening, is 100% or 1. Right. So probability is a number between 0 and 1, and it describes the likelihood of something happening. We're going to work at first with equally likely outcomes. In fact, we already have the coin flip with heads and tails. Those are equally likely. The fair die roll, rolling one die once and recording the number. Those outcomes, 1, 2, 3, 4, 5, and 6, are all equally likely outcomes. I'm going to write that like this. For the fair die, the probability of 1 is equal to the probability of 2 is equal to the, you see where I'm going with this, they're all equal, is equal to the probability of 6. Those are all equal to 1 out of 6. There are 6 things that can happen. They're all equally likely, so the probability of any one of them happening is 1/6. And also, this is what makes it a fair die. A fair die is one where all the sides are equally likely. A loaded die will make one of the sides more likely and another one of the sides less likely. But that's not an equally likely situation. The other one is the fair coin that we saw. The probability of heads is equal to the probability of tails. That's what it means to be fair. Since there's only 2 outcomes, the probability of each of those outcomes is 1/2. We'll see this a little bit later, that we can add probabilities, and if we add them together, the probabilities of heads and the probability of tails, we get 1. And here's an equation that describes, in terms of the numbers of equally likely outcomes, so that's the end of my example there. When all outcomes are equally likely, and by that I mean all outcomes in the sample space, everything that can possibly happen, each one of those outcomes is equally likely. The probability of the event is equal to the number of outcomes in A divided by the number of outcomes in S. And I think this is a better definition of probability than the previous ones. The probability of an event A is the number of outcomes in A. It doesn't matter which ones there are, it just matters how many there are, divided by the number of outcomes in the whole sample space. Again, it doesn't matter which, well, that's everything, but all of them. This works for equally likely outcomes, but it is a good place to start for studying that number that represents the probability. So I'm going to return to the fair die example. And in this example, we'll roll a fair die once. Let A be the event that the roll is less than 5. And what I'm going to do with this is, first of all, write down what that event looks like. We could write down the samples, actually, but let's focus on the event first. So less than 5, 1, 2, 3, and 4. 5 is not less than 5. So this event A is 1, 2, 3, and 4. If I roll a 1, a 2, a 3, or 4, that will be event A. A 5 or a 6 means it's not event A, but the other thing is the sample space is the same thing we saw before, the numbers 1 through 6. And it's really easy to tell how many there are in there. It's 1 through 6. There's 6. This one we can count. There's 4 numbers that are less than 5. Or there's 4 numbers in our event A. So I'm going to be able to find the probability of event A by the formula that I just had on here, the number of outcomes in A divided by the number of outcomes in S. So the probability is 4/6, or if I reduce it, it's 2/3, or if I wanted to have it in a decimal, it would be 0.67 if you round it to 2 places. 0.6 repeating, really, but this is sufficiently close. In fact, this is one of the advantages of fractions. It's easy to write it like this and have the exact value, whereas here I had to round, although with this one anyway, it's not hard to write it in exact value if you use the repeating bar notation. All right, so next we're going to look at how to combine events and find the probabilities of more than one event in more than one way. So these are called compound events. And we'll start with the OR event. And I'm going to use the notation that the book uses, which is to use the capital word OR. There is a mathematical logic symbol that's often used for this called the union symbol, but I'm going to stick with this because it's what the book uses. It looks like this. A or B is the event consisting of all outcomes in event A, event B, or in both A and B. One or the other or both situation is what the OR means. It's also called the inclusive OR. Not the kind of OR that you're using when you ask your child if they want spaghetti or a sandwich. Not one or the other or both. You want them to choose. That's the exclusive OR. This is the inclusive OR. And the other one is the AND event. And these are distinct from the words and or. They come from the words or and and, but they don't have exactly the same meaning. This one is strictly the inclusive or, and this is, I guess you could call it like the exclusive and, but it really means both of them. And let me put it this way: A and B consists of all outcomes that are in A and also in B. So this and is sometimes called the intersection, but I'm going to call it and to be consistent with the text. It means the overlap of the two events. The set of outcomes for A and the set of outcomes for B, anything that they have in common, that is what the and is. It's the overlap. And it's actually going to be easy to see. I'll mention this now because it's a good place to get started looking at these things. This is a Venn diagram. And if these are my events, A and B, then this little lens-shaped portion where they intersect, that represents the event A and B. Any outcomes in here is in this event. Any outcomes that are in the whole, I could draw it for the or event. Any outcomes that are in both, or in one, or in the other. That's what the or means, the inclusive or. And I have an example to demonstrate these. Yeah, we'll just look at these two for this first example to demonstrate the compound events. And that's, for this example, I'm going to have my event A be the outcomes 1, 2, 3, 4, 5. And event B, the outcomes 4, 5, 6, 7, and 8. And you can tell right away that this is not rolling a die because there's no 7 or 8 on the die. This is something else, and it doesn't matter where it came from. It's just that it's a situation where all the outcomes are equally likely. And in fact, I don't even want to worry about the probabilities right here. I just want to focus on those two compound event symbols. So let's look at A or B and not worry about the probability, but just what is that event? Well, the outcomes that are in A or B are the outcomes that are in event A or in event B or in both. And you can see there's a couple that are in both events. Those are the numbers 1, 2, 3, 4, 5, 6, 7, and 8. So that's the or compound event with A and B. The other one, A and B, the elements that are in A and also in B, are just the 4 and the 5. Those are the only numbers that are in both of these events. So that's the and event. Next, we're going to look at the complement. A prime is pronounced, so it's like an apostrophe up at the right. It's called a prime, but it looks like an apostrophe. A prime is how it's pronounced. This consists of all outcomes that are not in A. So the complement is the set of the outcomes that aren't in the given set. So the complement of event A is all the outcomes that are not in A, all the outcomes in the sample space that aren't in this event. This is the complement, like you may have seen in geometry. Complementary angles are two angles that form, when you put them together, they form a 90-degree angle. Complement, that's the same complement. If you and your coworker have different sets of skills, but when one of you is not doing as well, the other one can take care of that. That's called complementary skill sets. It does not mean your hair looks nice today. That's complement with an I, and that's a different word. It's pronounced the same, but it's a different word. This is complement as in you complete me. Anyway, what I want to point out about this is just this note. The probability of A plus the probability of A complement, or A prime, is always equal to 1. So in a sense, A and A prime divide the sample space into two pieces that complete the sample space. Complete. Here's a quick example of complement. For the sample space, S equals 1 through 6, the numbers 1 through 6, and event A equal to just 1, 2, 3, 4. This is actually the one that we looked at earlier, the set of outcomes from 1 to 4. A complement is equal to all the things in the sample space that are not in the set A, or all the outcomes in the sample space that are not in the event A. And that's just 5 and 6. Those are the two numbers that are in the 1 through 6 that aren't in the 1 through 4. I'm going to go a little bit further with this example to actually start to look at some probabilities. So what I'm doing here is assuming equally likely outcomes. If we assume that these 6 outcomes are equally likely in the sample space, like it would be for rolling a fair die, the probability of A is 4 out of 6, because there are 4 outcomes in A out of 6 possible outcomes. Of course, you could reduce that. I'm not going to, though. See why in a moment. The probability of A prime is, there are 2 outcomes in A prime out of 6 possible outcomes, so that's 2 out of 6. And what I want to demonstrate here is this note that I made, that the probability of probability of A plus the probability of A prime, which in this case is 4/6 plus 2/6, that's equal to 6/6, which is 1. And that's what it says in the note here, that the probability of an event plus the probability of its complement should be equal to 1. This is also why, I guess if I had reduced these, I'd still be able to add them pretty easily. But if you wait to reduce your probability fractions, it might come in handy that they have the same denominator later on if you want to check that the probabilities add to 1. So far with compound events, we've had the OR event, the AND event, and the complement. Next, we're going to look at conditional probability, and condition is the word. That's the key word here. Conditional probability of an event. It's on the condition of something else happening. So it's kind of like a more informed probability. But conditional probability of event A given event B is the probability of A given that B occurs. Either has already occurred or we know it's going to occur or something like that. As long as B occurs, sometimes it will change the probability of A. And that's what's meant by the conditional probability. B is the condition in this case. B is called the condition. And now the notation for this is, you have to be careful with this. This is very different from the other function notation that we've done and that you've probably done before. The probability of A given B. So this line within the probability function, I made it kind of exaggeratedly tall, but I do want it taller than my letters so I can just tell that it's a different kind of symbol. It's not a letter. It's not a capital I or anything. It's a divider that's read, well, you can read this whole thing as the probability of A given B. The probability of A given B. So the best way to pronounce that line is as the word given. It's the condition that it separates. The condition again is the event that's given to happen, the known event that did occur or is guaranteed to occur. The event of interest here is the probability of A. Now this is different from just plain old probability of A, but we are discussing the probability of A. In this case, in light of the given event B. So there's a way to calculate this, a formula that's really useful. Sometimes we have to calculate it a different way because we don't have all the information for the formula, but usually the probability of A given B is equal to the probability of A and B divided by the probability of B. And it's always this condition B that appears in the denominator. This numerator is a little bit flexible because you could have the probability of A and B or the probability of B and A. If they're in the reverse order, it doesn't make a difference there. But the condition is always the probability in the denominator. All right, so I've got an example. Yeah, I have an example that I want to take up the whole board for. We're going to use this formula, and I'll write it down again when we need to use it. So for this example, roll a fair die once. The sample space, again, we've seen this before, it's 1, 2, 3, 4, 5, 6. Let event A be 2 or a 3, and event B be 2, 4, 6. So that's my situation. I've got the sample space 1 through 6. Event A is defined as rolling a 2 or a 3, and event B is rolling a 2, 4, or 6, or as we saw before, that's an even number. Those are the only even numbers on the dice. Our problem here is to find the probability of A given B.
Last name is Broussard, B-R-O-U-S-S.
So to do that, I'm going to use the formula. The probability of A given B is equal to the probability of A and B divided by the probability of the condition B.
Okay.
So in order to find this probability of A given B, I can find the probability of A and B, and then the probability of B. Put them together and have a result for this. I think I can do that
Okay.
off to the side here. First, A and B. What is A and B? It's not a number. It's a set of outcomes. It's an event, a new event built from A and also B, and it consists of the things that are in both of these, which is just the number 2. The 2 is in A, the 2 is in B, and nothing else is in both of those sets. So A and B is just the outcome 2. And then the probability of A and B. Remember, this is a fair die. Each of these outcomes is equally likely. There's one outcome out of 6 possible outcomes. The probability is 1/6. The other thing I need, I'm going to box this off here. The other thing I need is well, there's B. I don't have to write B or find B, it's right there. But I do need the probability of B. And that's, there are 3 outcomes out of the 6 equally likely outcomes. So the probability of B is 3/6. We could reduce that, but let's not. It'll save us some time. When we do this, fill these in, the probability of A and B is 1/6. The probability of B is 3/6. So to divide by a fraction, I'm going to multiply by the reciprocal of that fraction. The 6's cancel here and give me 1/3. So the probability of A, given that B occurs, is 1 out of 3, or 1/3. And I think the fraction is fine here. You could put 0.3 root 3 in also. So another way to think of this that's not very mathematical, but if B occurs, so given B, if B occurs, it's either a 2 or 4 or 6. What are the chances that it's going to be an event A if we know it's one of those 3 numbers? Well, each of them is equally likely. And there's the 2, the single 2 out of the 3 numbers, 1 out of 3 is the same thing. So you can do that without the formula, but usually the formula is easier to keep track of because we're kind of dividing it into sub-problems and building it back up rather than trying to reason the whole thing at once. So the next example I have is another numerical example, but it's not specifically something like rolling a die. We're going to have equally likely outcomes and compute some associated probabilities. In this example, S is equal to the whole numbers starting with 1 and less than 20. With equally likely outcomes. And I am going to write this in set notation as a list, but that'll be actually part of the problem. The other thing is A is the event, the number is even, so an even number, and then B is going to be the event, the number is greater than 13. So if you can, record that. I'm going to have to, I've got it here, I'll use the same thing, but we're going to have to come back to these events because the first question just asks about, so part A just wants to know what is the sample space. The sample space is described verbally right here. Now I want to list it or write it in set notation. The numbers starting with 1 and less than 20, that's 1, 2, 3, all the way up to 19. So less than 20, not less than or equal to 20. So we're only going up to 19 with those whole numbers. Okay, I think I can fit this. Part B asks us to find A and B in this set or list notation. So A is the event the number is even. So the even numbers that are in this sample space are 2, 4, 6, 8, 10, 12, 14, 16, and 18. All the other numbers are odd. For B, the number is greater than 13. So greater than 13, that does not mean 13. That's 14, or 15, 16, 17, 18, or 19. So the number's greater than 13, not greater than or equal to, but going all the way up to the list. And it's only the whole numbers because we're just working with those in the set. I think I can write this next part up here and we can still refer to our lists at the bottom instead of the verbal descriptions. And for part C, I want to find the probability of A and the probability of B. These are actually going to be pretty quick because we've got those sets here. We've got a kind of a picture of the sample space. I really didn't list them all out, but it's really repetitive. It's just the numbers 1 through 19, whole numbers. But for the probability of A, with equally likely outcomes, I want to use 1, 2, 3, 4, 5, 6, 7, 8, 9 even numbers divided by 19 total numbers. And that's the probability of A. The probability of B, well, there are 1, 2, 3, 4, 5, 6 numbers in event B, 6 outcomes in event B, out of 19 total possible outcomes. And those are the probabilities of A and B. For part D, we're going to find A and B, and we're also going to find A or B. So A and B, the numbers that are, or the outcomes that are in both A and B. Well, it's really, since A is all the even numbers, I really just have to get the even numbers that are in set B, or in event B. 14, 16, 18, that's it. 14, 16, 18. And for A or B, that's in A or B or both, I've got definitely all the evens because they're in A, and then these numbers greater than 13 in here. Let me just list up the numbers from A that are up to 14. 2, 4, 6, 8, 10, 12, 14. But then, well, 16 definitely, but also 15 because it's in B. 15, 16, and 17, and 18, and 19. So those are the numbers that are in one or the other or both. Kind of a big list, but I think all we have to do is count them from here on. Part E has the probability of A and B and the probability of A or B. And we've got the sets listed, we've got the events listed here. These sets are listed out. We can just count and divide. Remember, there are 19 outcomes altogether. For A and B, there's 3 outcomes in the event out of 19 total possible equally likely outcomes. For A or B, I have to count up these. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those, again, out of 19 total possible outcomes. So once we've got the sets listed down, the events written down explicitly, it's really just a matter of counting to find the probabilities. For part F, F has a couple things. First, we're going to find A prime, and then we're going to find the probability of A prime. So this is A complement. All the events that are not in event A. A is the even numbers, so the ones that are not in A, the complement, are the odd numbers. Starting with 1, 3, 5, 7, 9, 11, 13, 15, 17, and 19. And there are 10 of those out of a total number of possible outcomes, 19. So the probability of A prime is 10/19. Again, because these are equally likely outcomes. This next, I'm going to leave that one little piece of our previous problem. Because part G tells us to find probability of A plus probability of A prime. And I can tell you what it should be. If you add the probability of an event and the probability of its complement, it should always equal 1. Here we get a chance to see that, I hope. Probability of A is 9/19. That's why I left that there. Probability of A complement is 10/19. That adds up to 19/19, which is 1, as it should be. Finally, I am going to take all this stuff down to do this last part because it's 2 side-by-side things. We're going to compare, and you'll need what you've already got for this. I've got it here. I'll write it down, but it's coming from the things that we already did. For part H, the probability of A given B is, from the formula, probability of A and B divided by the probability of the condition B. We found both of those. Probability of A and B is 3/19, and the probability of B is 6/19. So that's 3/19 times 19/6. The 19s cancel. 3/6, or 1/2, or 0.5. Actually, yeah, I continued it down to the 1/2. In lowest terms, it's the easiest comparison because there's only one way to write a fraction in lowest terms. Whereas if you don't require that, there's actually an infinite number of ways to write this fraction. It's a little harder to compare. For the other one, the probability of B given A, that's the probability of B and A, or A and B. We called it this before, so let's call it that again. Divided this time by the probability of A, because A is the condition, B given A, or B under the condition A. The condition is A. This one, A and B is the same as before, 3/19. Probability of A was 9/19. So that's 3/19 times 19/9. 19s cancel and I get 3/9, or 1/3. And here's my point. That's the point of this this problem. And they actually say, are they equal? And the answer is no. It's not that these two probabilities probability of A given B and probability of B given A. It's not that they can't be equal. They sometimes are, but sometimes they are not. And this is a case that demonstrates that they don't have to be equal. And I would say that typically they are not equal. That it makes a big difference which event you're looking at and which condition you're using. All right, it's going on 50 minutes, but I have one more example, and it's a little more fun because it's something we can relate to a little bit more easily. It's about handedness and, a survey of handedness and sex. So, in this example, I'm just going to call it a survey of handedness. And the data is given to us in this table where we're going to have 2 rows and 2 columns, but keep in mind a table with 2 rows and 2 columns really has 3 rows and 3 columns because of the labels for those. The data is going to fit in the middle, but we're going to look at right-handed and left-handed and male and female. So these are 2 characteristics that each individual has. It's a simplified situation. I know some people can use both hands and some people are intersex, but this is for the purposes of our probability experiment. And in the survey, here's the data: 43, 9, 44, and 4. And I think that's a much better way to have it than a list or a verbal description. Having it in a table like this, I can see there are 43 right-handed males. There are 9 left-handed males, 44 right-handed females, and 4 left-handed females. I do want to do something further with this table, but this is what's given. In fact, let's come back to that. Let me type out the experiment here. So an individual is selected at random from this pool of people. We're going to have 4 different events of interest: M, F, R, and L. And M is going to be the event that person is male. And there could be a whole lot of writing here. I'm going to use ditto marks. If you want to take the time to write it out, that's fine. But event that person is female, rather than write the same words over and over again. Event that person is right-handed. And finally, L, event that the person is left-handed. So these are the events we're looking at when our experiment is to select one individual. This is the data. I'm going to erase this, but I'm going to rewrite it in a more compact way, but then also extend it in a way that'll be useful. So that's the code, and it's pretty straightforward, MFRL. In fact, if I just use those for the labels on my rows and columns, I think it'll be even easier to read. So my label column, my left column, is just going to have M and F, and I'm going to keep going down. I am going to add another row. Then I'll have R and L for my two columns. I'm going to have another column also. And let me mark those off so they're all distinct. My original data, 43, 9, 44, and 4 fits in like that. And then the rest of these spaces, this is going to be a total column, the row totals. This is going to be a total row, the column totals. And this is going to be a total. That's everybody all together. But these separate things have meanings, though. This row represents the males. There are 43 right-handed and 9 left-handed. That's a total of 52 males. That's the total number of males. Females, there are 44 right-handed and 4 left-handed. That's 48. Also, if I add the males and the females, I get 100. There's 100 individuals here, which it didn't say in the problem, at least that I had it, but it's in the table. We can also check the total number of right-handed persons. That's 87, and 13 left-handed persons. You can also add across this, the number of right-handed plus the number of left-handed is also 100, because it's 100 people and they all have a handedness. This is what's sometimes called a contingency table. A contingency table. It's it's called a contingency table because it lets us do conditional probabilities. So under conditions or contingencies, we can calculate probabilities using this. And that's what we're going to do for there's a lot of parts to this example, but they're all going to come from this table. So I'm going to leave the table and just use the space down here. First of all, for A, to calculate the probability that the randomly selected individual is male. And that's, well, how many males are there? The total for the male row is 52 out of 100 individuals total, and that's it. I'm not going to reduce these, but I do want to point out that this, because it's divided by 100, it's really easy to put it in to decimal form. Just move the decimal point twice. But you can also see that it's a probability because it's a number greater than 0, less than 1. For part B, we're supposed to find the probability that the person is female. Similarly, there are a total of 48 females out of a total of 100 individuals. We're finding all the basic probabilities for the given events. First, the probability of R, the probability the person's right-handed. There's 87 right-handed people. 43 males and 44 females, but 87 altogether out of 100 total people. So 87 over 100, or 0.87. Part D asks for the probability of L. Left-handed, there are a total of 13 left-handed people out of the total 100 people. E asks for the probability of M and R. So this is something we can actually get from the table very easily, as long as it's a completed contingency table. The original data is just this middle part, and that was actually sorted in just such a way. M and R is those 43 individuals. There are 43 right-handed males, and that's what the AND event here means. 43 out of the total 100 people. Here's another similar one for F. The probability of F and L. Probability of, that's kind of scrunched, it looks like Fandle. But the probability that the person is female and left-handed. Female and left-handed, there's only 4 left-handed females out of this whole group of 100. So if we select one at random, the probability is 4 out of 100. By the way, that's 0.04 or 4%. But 4 out of 100 is a good way to write it. 1/25 if you reduce. All right, let me get some room from this. Next, for part G, it says the probability of M or F. So this is an OR probability. I'm going to write a little bit more for this one just so you can see where it comes from. But it is kind of a strange question. What's the probability that your randomly selected person from this group is either male or female? And it should be 1 because they're all males or females according to the data. So I'm going to write it this way. There are 52 males and there are 48 females out of 100. That gives me 100 out of 100, which is 1, a probability of 1. It's an example of a certainty. This compound event, M or F, is a certainty because its probability is 1. For H, we've got the probability of M or R, and that's, so M or R, and that's the inclusive OR. It means male or right-handed male, both. Well, I don't want to use the male total because that would, well, yeah, we should include the 9 here because they're males. We should also include these 44. They're not males, but they're right-handed. And what we actually need is the 43 right-handed males plus the 44 females that are still right-handed, because there are, and also the 9 left-handed males because they're males, divided by 100. That adds up to 96 over 100. Part I says they want the probability of F or L. F or L, so female or left-handed. That means female or left-handed or both left-handed female. We're going to do it the same way though. The left-handed females, definitely, they're both. But the females that aren't left-handed, because they're females, and the left-handed people that are male because they're left-handed. This is F or L, so they're L. And we need to include all 3 of those sets of individuals to get the entirety of the event F or L divided by 100. That comes out to 57 over 100. The next one I have is part J. Says the probability of M prime, that's 48 out of 100. And that's because M prime is F in this case. All the people that aren't males or females, it's those 48 out of 100. So the probability of M prime, it's actually identical to probability of F, because those are really the same event. JK gives a probability of R given M. I'm going to use the formula, the probability of R and M divided by the probability of the condition M. And I think we already calculated this. We called it M and R, but R and M is the same thing. And that was in part E, 43 out of 100. And then divided by probability of M, that was the first thing we did, 52 out of 100. Yeah. So if I multiply by the reciprocal, 43 over 100 times 100 over 52, I get the hundreds cancel and I get 43 out of 52. And it's worth noticing here, this isn't a hundredth anymore. The other ones we looked at were all over 100. So it's not as easy to change this into a percent. But what's important is this number is less than 1. The numerator is smaller than the denominator. It's positive, so it's a probability. Part K. Part L is to find the probability of F given L, and that's the probability of F and L divided by the probability of L. These, I think, are things that we already found. F and L, yeah, that's 4 100ths, and probability of L is 13 100ths. So when I simplify that, 4 hundredths times 100 13ths, that's 4 13ths. And then finally, part M says the probability of L given F. And this is another one of those comparison situations where they're trying to get us to look at something different, to emphasize that it's a different thing. If you switch the order with the and, it's the same. If you switch the order with the or, it's the same. If you switch the order with the conditional probability, it's usually quite different. So this one doesn't switch, does not commute. According to the formula, this is probability of L and F divided by the probability of F, which I think we found probability of F and L. Yeah, we called it 4 over 100. Probability of F is 48 over 100. And reducing those fractions like we did before, we're going to get a 4 upstairs and a 48 downstairs. That can reduce, but the point here is those are different. Reversing the condition and the event results in a different probability because they're different events.